Hey physicists, there are two questions in our Apply lab that have really kind of thrown people for a bit of a loop. Just want to review them here. The first one was this, right after the Pulley portion, and that was explain any differences between the input and output work in your data. This is pretty representative of the data that you saw, that we end up doing more input work than output work. They could be the same, but most likely you're finding a little more input work than output work. We saw an example of that with the bowling ball demonstration in class. The bowling ball did not come back as high after releasing it. The other place you would have seen this was when you read section 7.2 in your text on simple machines. That gives you particularly some information on pulleys. Okay. Let's see. Let's take a look where some of this work did go. Our input work, most of it went into the output work. We can see in the data I have here, of the 2 joules of input work I did, 1.8 joules went into the output work, which becomes potential energy. So we're really worried about, hey, where did that other 0.3 joules go in all this? Okay. Think about our observations. Okay. Hey, one is, we could take a look at, we know that any type of a system that has sliding, okay, we're going to end up seeing some type of thermal energy from the friction. Although there are pulleys in this system, they are not perfect pulleys or bearings, so the frictional force times the distance generally leads to thermal energy. Take your hands, rub them together, that frictional force generates energy. Another place you may want to consider, okay, as you're raising and lowering this, you probably heard the bearings rolling around. Okay, so that would be, if you heard that, you know that there is some of the energy that went into sound. Consider that. If you didn't hear it, then there would be an example of not having any energy in sound. But if you could hear it, sound energy would be another place. Okay. Another place, and that is, most of you who did your measurements carefully, you found that as you stretched the string or pulled the string, you had to pull more than, let's see, what was required to raise the block. For example, if I end up wanting to raise this 20 centimeters, if I had 6 strings, okay, each string gets 20 centimeters shorter. So 6 times the 20 centimeters, I would expect I'd have to pull my string 120 centimeters. Those who are doing careful measurements, I noticed a lot of people were around 1.22 to 1.23 meters. Okay, what about that extra 0.02 to 0.03 meters? That was stretch. You're still providing a force. Okay, so another place that could go into is the stretch of the string, and we could call that elastic energy. Okay. So far we've been referring to all these as dissipated energy, but this one really says, hey, explain any differences. Don't just stop at, hey, it's dissipated energy. What do you end up seeing or hearing that gives you evidence that there's dissipated energy? The second question that was giving people a lot of trouble was this one here, the third question for the ramp lab. Explain any differences between your gravitational potential and your kinetic energy in your data. So it's not just saying explain the difference between potential and kinetic energy. It's saying in your data you're going to find differences, explain those. Okay. Hey, as we'd expect, you know, this data here, and most of you had something like this, that the gravitational energy is slightly larger than the kinetic energy. And we'd expect that, just like with the bowling ball. I can only, or the skate lab. The maximum amount of energy I can have, or the total energy in the system, is, in this case, 0.185 joules. I know where most of that went. I know where 0.162 joules of that went, but what about that difference? We have a difference here of, what is it, about 0.02 joules. What ended up happening? We know it's no longer gravitational energy because it's all the way at the bottom here. Most of it is kinetic, so we know that it went into some form of dissipated energy, but what is the form of that dissipated energy? Hey, as we know, when we roll our cars along this track and it's horizontal, that there is some friction. Okay. Even though they're fairly low friction, there is some friction which leads to thermal energy, just like when we rub our hands together. We end up getting thermal energy. Okay. Some of you indicated there might be some noise. I don't find them making a whole lot of noise. There might be a little bit. If you can have evidence of that, that's fine. But the other thing I wanted you to point out or to see was, if you go back to our video when we were looking at the trampoline athlete bouncing up and down, initially they had this much gravitational potential energy. After they bounced a few times, something happened where they only had this amount of gravitational potential energy. At the time I was saying, hey, there's a big difference. At this point, the person is not doing their routine. Over here, the athlete is doing their routine. Something you'll notice here, once they go into the routine, you can go back and review this, is they start rotating or spinning. Okay. If I'm spinning, every part of me is moving. It means every part of me still has a form of kinetic energy, but it's this rotational energy. So in the car, as it goes down here, think about what is still spinning or rotating. Okay. Think about that for a moment. Think about in race cars, why they might spend a whole lot of money on very light wheels. Okay. Yep, you probably thought of it already. Yep, the wheels are still spinning, right? The wheels spin, okay, which gives them a certain amount of rotational energy. At the time I was saying, hey, we're not going to study that quantitatively, but we should know that that's another form of energy. If something is spinning, that's going to be a form of energy, just like if something's shaking back and forth, that's going to be a form of thermal energy. So take a look at that. Unless the car was on skis, those wheels are rotating, and that rotation is going to store some of that energy. Race cars have light wheels for that. Bicycle riders get very light tires, and even your Tour de France riders actually get slightly smaller wheels, so they don't have as much of this rotational energy. Okay. Those should help you out with those two questions. Get that lab turned in, get full credit, have me review it. Okay, do a good job on your draft too. All right, good luck on your test.